Swayam Prabha. Digital India. Educated India.
Hello everybody. Today I am delivering lecture 2 of the module 9. In the last class I have introduced the membrane theory of surface of revolution, and the surface of revolution is formed by rotating a plane curve around an axis of rotation, and this plane curve may have any nature. It can be a arc of a circle, or it can be a part of a parabola or ellipse, and accordingly the surface of revolution is named. So, today I will discuss a surface of revolution which is formed by rotating an arc of a circle, and it is commonly known as spherical dome. So, today our discussion will be membrane analysis of spherical dome subjected to gravity loading along the surface of the shell, and also the loading which is spreading over the horizontal plane of the shell. So, two types of loading we will consider, because in the latter case the snow loading is applicable. Snow loading is generally specified in terms of loading over the horizontal surface. Okay. Now, the spherical dome is formed by rotating a part of a circle, a circular arc around an axis of rotation that you are seeing here, and this arc is known as meridian. Now, as a result of this circular arc rotating about an axis of rotation, the curvature along two principal directions are same, and the radius of curvature of the shell, that is the principal radii of curvature r 1 r 2 is now equal to the radius of the sphere. And you can see at any level we have a parallel of latitude that is also a circular in plane, and it has a radius which is different from the radius of the sphere, but this radius can be related to the radius of the sphere by trigonometrical relation. Now, in case of membrane analysis of shell, we are basically dealing with the three quantities. One is n phi, and another is n theta, and another is n theta phi. In general, n theta phi also exists for any type of loading, but when the axisymmetrical case is considered, that means loading is symmetrical about an axis of rotation, then we neglect n theta phi. So, the only quantities that have to be found out are n theta and n phi. N phi is the membrane stress along the meridional direction, and n theta is the membrane stress along the tangent to the parallel circle. So, that is the circumferential stress. So, for axisymmetrical cases, if you recall, we arrived at two equations of equilibrium. In general, there are three equations of equilibrium, but because of n theta phi equal to 0, second equation becomes meaningless, and we now have to deal with the first two equation. So, first equation gives after integration this value of n phi, and third equation, that is actually an algebraic equation. So, once the n phi is found for the given loading and given geometry of the shell, n theta can be calculated. You can see this equation here, it is second equation which relates n theta to n phi, via radius of curvature of the shell, and this is the third equilibrium equation. Equilibrium condition is taken here along the normal direction, normal to the tangent plane at the meridian, any point in the meridian, and W r is the component of the load along the normal direction, along the radial direction. So, we call W r as the radial load. That means, component of this load that is acting over the surface of the shell along the radial direction, and there are other components that W phi along the meridian direction, whereas W theta is taken as 0. So, these are the cases we have to consider here, and you can see this integral n phi is 1 by r 2 sin square phi. Then integration you have to do r 1 r 2 W r cos phi minus W phi sin phi into sin phi d phi plus k. K is a constant of integration. Generally it is a indefinite integral. So, we put a constant of integration, and when for a closed shell the limit of integration becomes 0 to at any level of latitude that phi, then constant becomes 0. So, we take constant k equal to 0. So, therefore, we find the integration of this expression with a limit 0 to phi if the shell is closed, and we can obtain the value of n phi. Okay. Now, remember that for spherical shell, this r 1 equal to r 2 and r 2 and r 1 now becomes the radius of the sphere. Okay. So, multiplying both sides of the equation 1, that is the equation 1, I multiply both sides of the equation 1 by 2 pi sin phi. So, multiplying both sides of the equation by 2 pi sin phi, then we can get this equation as 2 pi r 2 sin square phi n phi, that is r 2 I have taken here, equal to integration of this 2 pi r 1 r 2 multiplied by W r cos phi minus W phi sin phi into sin phi d phi plus 2 pi k. 2 pi k is again the constant, previous constant was k and it was multiplied by 2 pi. So, now the constant stands at 2 pi. Okay. However, the constant of integration here is taken as 0 for closed shell. Okay. Now, you can see here a spherical dome that has to be analyzed for the gravity load W g. W g consists of self weight of the shell and live load, specially if there is a live load on the shell, that is for maintenance purpose. If the shell is used for roof, then for maintenance purpose some live load will be there, but it will be very nominal. So, W g includes self weight as well as live load here, and it is distributed over the surface of the shell. Okay. Now, if you see that equilibrium equation have been obtained by resolving the forces into 3 directions. One is the phi direction, that is the tangent to the meridian, and second direction is tangent to the parallel circle, and third direction is normal to the parallel circle. So, with the 3 directional components, and when these are added and equated to 0, we get the equilibrium equations. Now, W g is your load that is acting vertically downward, but we have to resolve these forces along 2 directions, that is W r W phi, because W theta is not taken here. So, equilibrium equation along the tangent to the parallel circle here for axisymmetrical condition is not applicable. So, we take only the component along the radial direction, that is W r, and along the meridional direction, that is W phi. So, this phi is the angle that you are seeing here, which is measured from the vertical axis of rotation, and accordingly this angle will be phi, and therefore, component W r equal to minus W g cos phi. The negative sign is taken here because the normal direction outward to the surface of the shell is taken positive. So, therefore, it is towards the inward side. So, therefore, the negative sign is taken. So, W r equal to minus W g cos phi, and the component along the meridional direction is W phi is equal to W g sin phi. So, we write W r equal to minus W g cos phi and W phi W g sin phi, that have to be used in our first equation that I have shown in the integral form, and W theta is 0. Okay. Now, come to this equation that we have to now evaluate. N phi equal to 1 by r 2 sin square phi integration r 1 r 2 into W r cos phi minus W phi sin phi into sin phi d phi plus k. Of course, we will take k equal to 0 because the shell is closed shell, and under axisymmetrical loading condition there will be no membrane shear force, there is n theta phi. So, now substitute the value of W r W phi as we have obtained in the earlier cases by resolving W g into respective directions. What are the respective direction? One direction is along the normal direction and radial direction, and another direction is along the meridional direction. So, taking W r equal to minus W g cos phi and W phi equal to W g sin phi, then we take here W r is substituted in terms of W g and cos phi. Similarly, W phi is substituted in terms of W g and sin phi, and one is with minus sign. So, therefore, we take minus common and it becomes cos square phi plus sin square phi, and this sin phi is already there. So, we write it as sin phi into d phi plus k, and other quantity, that is r 1 r 2, r 1 equal to r 2. So, therefore, it becomes r square. So, we take it outside the integral sign because the radius of the sphere is a constant quantity, and in the numerator r is already there and sin square phi is there. Okay. So, cancelling this r square with r, that is dividing r square by r, we get 1 r, and then this term is 1, cos square phi plus sin square phi is 1, then remains only the integration of sin phi d phi and with the limit phi naught to phi. Now, for a closed shell, the limit is taken as lower limit is taken as 0. So, 0 to phi we have to integrate. So, now integrating sin phi, it will be cos phi and limit will be 0 to phi. So, after substituting the limit in the integral, then we get this n phi equal to minus r w g divided by sin square phi into 1 minus cos phi. This expression can be simplified. The sin square phi can be written as 1 minus cos square phi, and this numerator is already there 1 minus cos phi. Then after factorizing this, that 1 minus cos square phi can be written as 1 plus cos phi into 1 minus cos phi. Then 1 minus cos phi and 1 minus cos phi is cancelled, and then we only get n phi equal to minus r w g divided by 1 plus cos phi. Now, n phi is coming as negative. So, negative sign here is the compressive force and positive sign will be denoted for the tensile force. So, n phi we got as in terms of the radius of the sphere, and the w g, that is the intensity of the vertical load that is acting on the shell surface, and in terms of the meridional angle phi. So, you can see the nature of the n phi is compressive. So, for this type of shell, even if we construct it with reinforced concrete, it remains compression for any loading, that is vertical loading and meridional angle phi. For any meridional angle for the shell surface that we assigned in the design, it will remain compressive. So, that will give advantage to the design of concrete structure, because concrete is very weak in tension. So, if it remains in compression, that we have the advantage of designing the structure. So, once we obtain this n phi, then we substitute here and we can get n theta. Now, again note it that r 1 equal to r 2, and therefore, n theta from this equation we get w r into r 2 minus r 2 by r 1 into n phi. R 2 by r 1 is 1. So, therefore, n theta equal to w r into r 2 minus r 2 by r 1 into n phi. Now, substitute w r. What is w r? W r is the component of the load in the radial direction. It is minus w g cos phi. So, this expression is needed there. So, substituting w r here, and n phi equal to minus r w g divided by 1 plus cos phi into this expression, and r 1 equal to r 2, then we get n theta as w g into r into 1 divided by 1 plus cos phi minus cos phi. So, this expression for the circumferential stress n theta may be compressive or may be tensile depending on the value of phi, that we have to find out. Now, let us see, we take a hemispherical dome and examine the variation of n phi and n theta along the meridional angle phi. Now, we already noted that n phi, the meridional stress is always compressive for any value of phi. However, the value of n theta changes for certain value of phi, that means, nature of the n theta may change with the value of phi. So, therefore, we have to see at what value of phi this angle, this magnitude of the this nature of the n theta changes. That means, its nature is reversed. Previously, say it was compression, now it will be in tension. So, this angle we have to find out. Now, plane at where that n theta changes its nature or sign is known as plane of rupture. We generally intend to avoid the tensile force in the concrete structure. So, therefore, if we know the plane of rupture, we can limit our dimension in such a way that the phi does not exceed a certain critical value, so that tension is not developed in the shell surface. Okay. So, n theta is 0 if this quantity 1 by 1 plus cos phi minus cos phi equal to 0, because w g and r are non-zero constant. Okay. So, equating these to 0, we can solve for cos phi. Okay. So, this angle gives a quadratic equation in cos phi, and the value of cos phi now becomes one value is 0.61803, and this is only the value that can be accepted. Other value will be not relevant to the problem in question. So, therefore, the cos phi is found as 0.61803 and phi is 51.82 degree. So, now we get the limit of the angle phi up to which the shell remains under compressive force only. So, up to this level that I am showing here remains in compression. So, but the n phi, the meridional stress is compressive throughout the shell, throughout the surface of the shell, from the springing to the crown. This is the springing level and this is the crown level. So, here you can see the variation of n phi. If I draw from 0 to say phi, here it is phi is 0 and here it is phi 90 degree. So, that you can see in this expression, if you put phi is equal to 0 means it will be n phi will be minus r w g by 2, because cos 0 is 1. So, r w g by 2 will be the value of n phi at phi is equal to 0, and when phi is equal to 90 degree, that is cos phi is 0, then n phi will be minus r w g. In both the cases n phi is compressive, that is coming with a negative sign. So, therefore, variation of n phi we can see now r w g by 2 to r w g, okay. Because phi is measured from the vertical axis. So, here the phi is 0 and at this point it is 90 degree, and because of symmetry the same stress will be generated here also. Now, if I see the variation of n theta, this is the expression for n theta. So, at phi is equal to 0, here you are getting this 1 by 2, because cos 0 is 1. So, 1 by 2 minus 1, that is minus 1 by 2. So, at phi is equal to 0, we are getting this as minus r w g by 2. So, that is the magnitude of n theta at phi is equal to 0. Now, let us see at phi is equal to 90 degree. So, when phi is 90 degree, cos 90 is 0. So, therefore, n theta is w g by r, and it is coming as positive quantity. So, therefore, tensile. So, here you are getting the tensile forces are developed after this plane, and this plane is nothing but plane of rupture, and it is located at phi is equal to 51.8 degree. Okay. Now, this expression, this integral that you are seeing here, 2 pi r 2 sin square phi into n phi equal to this 2 pi r 1 r 2 w r cos phi minus w phi sin phi into sin phi d phi plus 2 pi k has some physical meaning. So, if I apply the physical meaning in some problem, we can readily obtain the expression without going for lengthy integration in some cases. So, now here we will try to give you the physical meaning of this expression. Okay. Now, if you see take a small strip of the shell whose width is r 1 d phi, and d phi is the small angle here, meridional angle d phi, and phi is here. So, this small angle is d phi, and this radius of the sphere is r 2 equal to r 1, and r is the radius of the parallel circle, which can be related to r 2. So, r can be written as r equal to r 2 sin phi. Okay. Now, you can see here the direction of n phi is along the meridian, tangent to the meridian. So, this is n phi, and this angle is phi again, because if this is phi, this angle will be phi. So, vertical component of n phi, if you see the n phi sin phi, and horizontal component is n phi cos phi. Now, come in this expression, this you are seeing that n phi sin phi term is here, is included here. So, n phi sin phi means vertical component of n phi here per unit length. Then the circumference of this parallel circle, that is 2 pi r, whereas r is equal to r 2 into sin phi. So, r 2 sin phi 2 pi r is the circumference of this parallel circle. So, that means, if I multiply the vertical component of the n phi, that is meridional force, n phi vertical component is n phi sin phi, with the circumference, that is the total length over which it is acting now at this level. So, you will get total vertical force at this level. So, total vertical force at this level is 2 pi r 2 sin square phi n phi. Now, this total vertical force at any level must be balanced by the this the external load. The n phi is the reactive force that is in response to the external load, that is gravity load. Now, if I see the right hand quantity which is under the integral sign, we will be able to find out the relation between this total vertical meridional force around the circumference and the total vertical load acting above that level. So, here you can note this quantity that if you take a small strip here for the shell surface, r 1 d phi into 2 pi r is the area of the strip. So, 2 pi r into r 1 d phi will be the area of the strip, and since r can be written as r 2 sin phi. So, total area of the strip is 2 pi r 1 r 2 sin phi. So, under the integral sign you will get these terms are there, 2 pi r 1 r 2 sin phi. So, that means total surface area is there for the strip. Now, inside the parenthesis the load component let us examine. So, load component W r is W g cos phi and load component W phi is W g sin phi. Now, here you can see the W r cos phi is the component of W r along the vertical direction, and similarly here W phi sin phi is the component of W phi along the vertical direction. So, the quantity inside the parenthesis indicates that it is nothing but the effective vertical load. So, effective vertical load multiplied by the area of the strip, because it is axisymmetrical loading. So, 0 to phi is taken as the limit of the integration. So, that means this quantity, the left hand side is nothing but the vertical component of this meridional force, total vertical component of the meridional force at a level phi, and it is equal to the total vertical load acting on the shell surface above that level. So, using this physical meaning we can solve many complicated problem without going to integrate the expression. Okay. Now, let us see whether we can get the same result that we have obtained by integration earlier. Using the integration, we obtain this n phi and n theta as this. So, let us see whether we get this by means of physical interpretation. So, for an elementary strip, area of the surface is, suppose this for example, this small angle is taken as d alpha. D alpha is taken only for avoiding the confusion in the integral, because the limit we are taking 0 to phi and integration is done with respect to phi. So, we are taking another variable alpha instead of phi, but the expression will be same. So, if I take this angle as d alpha and this strip width is r 1 d alpha, then total area of the strip will be r 1 d alpha into 2 pi r. So, that is we get this 2 pi r sin alpha r d alpha. So, r sin alpha is this can be taken because r 2 sin alpha and r 2 is nothing but r 2 r 1 is equal for the spherical shell. So, we get this quantity as the area of the surface. So, total surface area of the spherical dome is now found after integration from 0 to phi, and after integrating we get it as 2 pi r square into 1 minus cos phi. Now, total load at level phi is say W g is the vertical load acting on that, this W g multiplied by this surface area is the total load. Okay. So, we get one quantity that in the right hand side without integration we get this quantity appearing in the left right hand side by means of physical meaning. Then the vertical component of n phi, that is n phi sin phi is the component per unit length, and this is the circumference of the parallel circle 2 pi r sin phi. So, now equating this F b to W, we get now n phi equal to R W g 1 plus cos phi. So, again this same quantity is obtained by means of physical meaning and in which the integration is avoided. This technique is useful for some shell where discontinuity arises because of this cut. Some shell has some opening. So, because of discontinuity we cannot integrate this up to the limit. Therefore, it is not a closed shell and constant is not 0. So, in that case this application of this physical interpretation will be useful to obtain the stress resultant. Okay. So, once you obtain the n phi, then you can obtain the n theta. N theta can be very easily obtained because we know the relation n phi by r 1 plus n theta by r 2 equal to w r, whereas this n phi is obtained from this equation. So, n theta can be obtained simply by substituting n phi in the third equation of the equilibrium. Third equation of equilibrium is this equation. So, you can arrive at the same quantity that you have obtained by means of integration. This quantity is actually obtained by integration, other quantity is obtained by solving this algebraic equation n phi by r 1 plus n theta by r 2 equal to w r. Okay. Now, let us see how this shell responds to the load which is acting over the horizontal surface. Now, previously we have taken the load is acting along the surface of the shell. The surface of the shell is curved, but here the load is taken on the projected surface, that is the on the horizontal plane. So, W p is the load per unit area on the horizontal surface, and W, if you see only W is the load that is acting on the curved surface of the shell. Okay. So, how to obtain this the stress resultant due to this type of load? Now, here if you see, take a small length of the shell which is of length d s and the horizontal length is d x, and we take the unit width of the shell, then we can say that the total load, that is W p is the load acting along the horizontal projection. So, W p d x equal to W into d s, because total load is equal. So, by equating this we get W is equal to W p cos phi. How it is cos phi? Because d s by d x, that W is d x by d s, and d x by d s from this triangle you can get it is cos phi. So, the load here, this along the surface, that is the vertical load along the surface of the shell, we take W p cos phi, and its component along the radial direction is minus W p cos phi into cos phi. So, minus W p cos square phi, and along the meridional direction it is W p cos phi sin phi. So, W p sin phi cos phi is written here as the component of the load along the meridional direction. Okay. Now, we use the same equation. Let us do it by integration from the first principle. So, the membrane stress along the meridional direction is given by this integral, and that integral is found from the first differential equation. That differential equation was found by equating the sum of the forces along the direction of phi, along the tangent to the meridian, that is we call it phi direction. So, this integral is obtained, and we now use this the W r and W phi that we obtain for the projected load. So, by using this quantity W r is equal to minus W p cos square phi and W phi is equal to W p sin phi cos phi, we now write this equation and then we obtain this n phi by systematic integration of the quantity. I am showing you the full integration. So, this is r square divided by r sin square phi and then integration 0 to phi, and this quantity actually I have substituted here for the radial component and the component along the phi direction, and after substituting this component is the expression is converted in this form. So, taking this cos phi common from this parenthesis, we can now write say W p r divided by sin square phi minus cos square phi plus sin square phi into cos phi sin phi d phi. So, this quantity is 1. Now, cos phi sin phi, if I multiply it by 2 and then divide it by 2, then we can write it sin 2 phi, and this divided by 2, there is factor 2 is coming in the denominator here. So, now integrate this expression sin 2 phi, it will be minus cos 2 phi divided by 2, and then substituting the limit of the integration, we now get this quantity as W p r divided by 4 sin square phi, and after carrying out this simplification, that cos 2 phi can be written as cos square phi minus sin square phi, and this cos 0 is 1, but 1 I have substituted as cos square phi plus sin square phi, but it is under the minus sign. So, therefore, cos square phi minus sin square phi. So, we can now write this cos square phi will get cancelled here, and then sin square phi it will be minus 2 sin square phi. So, 2 will be divided here with 4, and then the quantity this expression for n phi becomes minus W p r by 2. So, this expression is found for the snow load, and membrane force n phi for snow load now becomes minus W p r by 2. Now, since W phi is obtained, we can now obtain n theta. The expression is this n phi by r 1 plus n theta by r 2 equal to W r, and W r as we have resolved earlier, it is minus W p cos square phi. So, after substituting all this value here, the n theta is calculated as minus W p cos square phi into r plus W p r by 2, and after simplification we can write it minus W p r by 2 cos 2 phi. Now, we can see the variation of n phi and n theta with the change of angle phi. Now, you can see here the n phi does not depend on the meridional angle phi for this type of loading, and it is a constant quantity and is always compressive. So, this is a peculiar result that we have obtained in case of the load that is acting on the shell surface. We are getting the variation of n phi with respect to phi. Of course, that time also we got this n phi as compressive throughout the variation of phi. Here also n phi is compressive, but it is a uniform quantity. N theta of course varies with phi, and let us see how it varies and where n theta changes its sign. So, it can be readily verified from this expression. So, when phi is equal to 45 degree, that is pi by 4, the n theta from compression changes to tension. So, the variation of this quantity will be like that. The n phi diagram is always compressive, and this n theta will be compressive, that is with negative sign up to 45 degree angle of phi, and then it will be tensile, and the variation will be nonlinear, but here the variation is uniform. Okay. Let us see one example which will clarify the theory that I have discussed. So, how this membrane theory of shell can be used to design a spherical dome, that will be illustrated with a numerical example. So, example is this: a RCC spherical dome has to be designed and the thickness of the dome is 75 mm, load including live load is 3.5 kilonewton per meter square, span of the dome is 12 meter, rise is 2 meter, and the spherical dome is supported over the periphery by a ring beam, that is the edge beam, and the edge beam concrete is M20 grade. Shell concrete also you can take M20 grade, and steel is Fe 415, and also following input are given. Permissible compressive stress in concrete is 5 Newton per mm square, and permissible tensile stress in steel 230 Newton per mm square, permissible tensile stress in concrete as 2.8 Newton per mm square. Okay. Let us see the solution of this problem. Okay. So, we have the thickness of the shell as 75 mm, and you can see that span of the shell is mentioned as 12 meter. So, in relation to span, the thickness is very small. So, it is a thin shell. So, let us find out this quantity, the design quantity. Okay. We have this shell, it is a spherical shell of very small thickness, but covering a large area, okay. And it is supported over an edge beam. At the edge it is supported by a beam. Okay. The span of the shell is given as 12 meter. So, this distance is 12 meter. You can take it from center to center of the edge beam. Okay. Rise of the shell, that is called rise, is given as 2 meter. Radius is not specified. Now, radius can be found out very easily, and shell is subjected to this gravity load along its surface. And this load is uniform load, it is 3.5 kilonewton per meter square. Okay. So, that is the geometry of the shell, and this is your edge beam. Okay. Now, if I see the geometry of the shell, let us draw a line diagram. Okay. This is 12 meter, and this is 2 meter, the rise of the shell. Then radius of the shell is still unknown. We have to find this radius. Okay. Say this is the radius r. Now, we can see here that r square, if I consider this triangle, then r square equal to, this side is r minus 2 whole square plus this distance is 6 meter, this is also 6 meter, 6 square. So, by solving this we get this r is equal to 10 meter. So, radius of the shell is 10 meter, which will be used for finding the membrane stresses. In the membrane stress expression, you need the description of the or the value of the radius of the shell. Okay. Now, let us examine whether the geometry of the shell permits any advantages for the RCC construction. That means, advantages I am implying that whether shell will be throughout compression or some tension will be developed. Now, we have seen that if the phi is limited up to 51.8 degree, then there will be no tension. So, let us find out what will be the value of phi. Okay. So, say this is the value of phi here, and we can see here that 10 phi tan phi can be calculated as 6, this angle is constant angle. So, say this is phi naught. So, tan phi naught is 6 by total radius is 10. So, 10 minus 2, that is 8. Hence, we get phi naught equal to, after calculation we will get 36 degree 52 minutes. So, it is less than 51.8 degree. So, hence there is no chance of any tensile stress in this shell. So, therefore, at any level the shell will remain in compression. So, that is our conclusion by seeing the angle. So, now we can readily find it. The expression for n phi is your minus w g r 1 plus cos phi. So, n phi increases with phi. So, the maximum value of phi is 36 degree 52 minutes. So, substituting this n phi, you will get w g is 3.5, radius of the shell is 10, and this is 1 plus cos 36 degree 52 minute. By calculating this, we get this n phi as minus 19.44 kilonewton per meter. So, shell remains in compression, and maximum value of compression, that is n phi, is 19.44 kilonewton meter. Okay. Now, calculate n theta. Okay. The expression for n theta we already derived, and this is found out as minus w g r divided by 1 plus cos phi w g r cos phi plus w g r divided by 1 plus cos phi. Okay. So, this is the value of the expression for n theta. Now, it is to be noted that n theta decreases with phi. So, maximum value of n theta is obtained when phi is 0. So, now maximum value of n theta is obtained as minus w g, if I put phi is 0, w g r, w g, this is g, w g r by 2. Okay. So, that means the maximum value of n theta is now obtained as minus 17.5 kilonewton per meter. So, we have got the maximum value of membrane stresses. N theta is this minus 17.5 kilonewton per meter, and also the n phi is 19.44, in minus sign is for compression, kilonewton per meter. Okay. So, with these two values, now we can go for design the shell. Okay. Now, if it is of reinforced concrete, then we can compare the stress developed in the section with the permissible stress in concrete. Now, maximum stress is this n phi. So, therefore, sigma phi is 19.44 into 1000, that will be in Newton, and then if I divide it by 1000, then again it will be converted to in Newton per millimeter. So, 1000, and thickness of the shell is 75. So, now we get sigma phi equal to minus 26 Newton per mm square, and this is less than the permissible stress of concrete of grade 20 that we used in this design calculation. So, therefore, the shell is safe. Maximum compressive stress developed is 0.26 and permissible stress is 5 H. Now, since the no tension is developed in the shell, in principle there is no necessary for any reinforcement, there is no need of any reinforcement, but you have to provide certain nominal reinforcement. So, nominal reinforcement at the rate of 0.15% has to be provided. So, AST at the rate of 0.15% of gross area is required, and you can see this gross area is found as thickness into 1000 millimeter square, that is, and at this rate the reinforcement 8 mm at the rate of 200 center to center is adequate. So, it is provided. So, how the shell reinforcement is provided? Suppose if I show you a section of the shell surface, reinforcement is provided at the middle surface. So, this is 8 mm phi at the rate of 200 center to center, and this is also same reinforcement distribution steel is provided, and thickness of the shell is 75 mm. However, this thickness may require to be increased at the edges, because there the membrane stress is not so much applicable. So, let us see the condition of edge beam. If we see the plane of the roof dome, there is a circular and this is your edge beam. Now, you can see here that at the edge beam, near the edge beam thickness is increased. So, the thickness earlier was 100, now here thickness is increased. So, increased thickness may be 125 mm. So, I am proposing the thickness at this edge is 125 mm compared to thickness as 75 mm at the other portion. Okay. So, reinforcement is here, that have to be brought inside the this edge beam. That have to be brought inside the edge beam. Now, let us see what will be the dimension of the edge beam and this reinforcement of the edge beam. Now, you can see the membrane stress n phi at this level of the shell have two component, one is n phi sin phi, another component, that is horizontal component, is n phi cos phi. So, n phi cos phi component will give you the tensile stress in the edge beam, that has to be taken into consideration for design of edge beam or checking the safety of the edge beam. So, this pressure is P on the edge beam and P is here n phi cos phi. This radius is here 6 meter, because the span of the shell was 12 meter. So, now we can get this tensile force on the edge beam as just like your hoop stress that you consider, it is tensile stress, tensile force at edge beam will be n phi cos phi into this radius is here your this r, this will be your this r sin phi. Okay. Now, cos phi sin phi can be combined and this can be written as half n phi r sin 2 phi. So, we can now get this total value of tension as half n phi we obtained at this level 19.44, and this radius of the shell is 10, and this r 2 phi sin r 2 phi. So, sin 2 into 36 degree 52 minute. This is equal to 93.3 kilonewton. So, this the ring beam has to be designed for this value. We are taking this. So, AST for ring beam is now found out. The total tensile force is 93.3 into 1000 divided by permissible stress 230. So, this area becomes 405 millimeter square. So, therefore, we can say that the AST of 405 square, that means if I provide 412 phi, that will be adequate, in addition to stirrup. Okay. So, 412 bar has to be provided and stirrup reinforcement will be there. The size of the beam can also be found out from the tensile stress criteria, and we know that total tensile force divided by the area, transformed area A into A plus m minus 1 into AST should not exceed the tensile stress, permissible tensile stress in concrete, that is given. Okay. Now, m is taken for FCK 20 Newton per mm square as 13. AST already we have found. AST is AS is equal to 4 into 412 millimeter bar, 4113. 113 is the area of 112 bar. So, that is 452 millimeter square AST. Hence, we get from this equation the quantity A, because Ft is found out earlier. Ft was found out as 93.3 kilonewton, that means 93.3 into 1000 Newton. So, A is found out as 88,152 millimeter square from this equation, minimum A required. So, that means the size of ring beam, H beam, which is a ring type, that is a circular beam, H beam is now taken as root over this, that is we take 300 mm by 300 mm size. So, design is completed. We found the size of the H beam, reinforcement of the H beam, the thickness of the shell that was adequate to resist the maximum compressive force, and we got the reinforcement in shell. Thank you very much.